Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to go through an example of using phasor diagrams to analyze an LRC circuit. So what we're looking at here is a resistor, capacitor, and an inductor with the following values connected to a sinusoidally varying voltage source. And this voltage source, we're going to use a standard United States outlet here that has a peak voltage of about 170 volts and an angular frequency of 377 rad per second. Now, a standard US outlet is a 120 volt, 60 hertz source. So here's where I'm getting the 170 and the 377. So 120 volts is, again, what's called the RMS voltage. Hopefully you've seen my video on AC circuits and resistors where I talk about that. It's the average voltage. The RMS voltage and the max voltage differ by square root of 2. So the maximum voltage is equal to root 2 times the RMS voltage. So I took the 120 volt RMS voltage multiplied by root 2. That comes to about 177 volts. I'm sorry, about 170 volts. All right, the US power grid is a 60 hertz source. Well, your angular frequency is 2 pi times your linear frequency. That comes to 377 radian per second. So I've already calculated these values. All right, so the next step here is to find the capacitive reactance and the inductive reactance. So let's start with the inductive reactance. So the inductive reactance, the X sub L, is equal to omega L, which in this problem is 377 rad per second, times the inductance of 100 millihenry. So when we go through and calculate this, I get 37.7 ohms. Now keep in mind, milli is 10 to the minus third, so this would actually be 0.1 henries. All right. The capacitive reactance, X sub C, remember, is 1 over omega C, and that's equal to, let's see, that's going to be 1 over, where'd my frequency go? Oh, 377 radian per second times the capacitance, which is 50 microfarad. And if you give me a moment here, I got to calculate a value for that. Okay. I'm calculating this out. I'm getting 53 ohms out of that. All right. So when you calculate this, if you're following along, don't forget, put this in parentheses, and don't forget that's 10 to the minus 6. All right, so now we've got a resistor of 20 ohms, capacitive reactance of 53 ohms, and an inductor of 37.7 ohms. So now I'm going to go ahead and start working on the phasor diagram. Got this great little drawing tool to use for this. Whoops. All right, draw that phasor diagram right here. Horizontal axis, vertical axis. All right, I always start when I draw a phasor diagram with the current phasor. And since I did the voltages in blue last time, I'm going to go ahead and do the voltages in blue. The reason I start with the current phasor, because I know that the voltage phasor for the resistor is in phase with the current. So there's the voltage for the resistor. Now, length of the vectors doesn't even make sense to compare them. Now the capacitor and the inductor, let's see. So the voltage for the capacitor lags the current phasor. So the capacitor's voltage is going to be down like this way. So voltage of the capacitor. The inductor voltage leads the current. So that's going to look like this. There's the voltage across the inductor. Now remember, this one can be written Ix sub C. This one can be written Ix sub L. And comparing the reactances, the X sub C is 53 ohms, and the X sub L is 37 or about 38 ohms. So this problem is going to be more capacitive than inductance. So when I add these, the net voltage phasor here is going to be like kind of down and right, because this one's going to be bigger than this one. So what I'm going to do here is I'm going to replace this pair with a single vector. That's down and right. And that vector is going to equal the voltage of the capacitor minus the voltage of the inductor. Right, now what I'm going to do is I'm going to move that vector. Oops. A little better job than that, hopefully. To here. And then draw in the resultant vector in blue. Didn't get a perfect 90 there, but that's okay. All right, so remember, this one is the V sub R. This one is the V sub C minus V sub L. This is the net. Okay, they are related by Pythagorean Theorem. I'm going to go ahead and make myself some room here. Okay, so the net voltage squared is going to equal V sub R squared plus V sub C minus V sub L squared. And now I'm just going to use, replace these now with, actually I'm going to square root both sides before I do anything. Now, the net voltage, remember, the entire circuit has a property called impedance. So when I apply Ohm's law to the net circuit, that's voltage equals I times the impedance. That's what this term is going to be. I times Z equals square root of, this term is going to be IR, and then squared, plus this term is going to be IX sub C minus IX sub L squared. Now you can factor an I out of all of these terms. It'll divide out with this one. So the impedance of the circuit is going to equal the square root of, and I have numerical values for all these. I'm just going to go ahead and put them in. So this is going to be 20 ohms squared plus, now by the time I factor out the I, we're just going to have X sub C minus X sub L. I'm looking for these values here. This was the capacitive reactance, 53 ohms. Minus 37.7 ohms. I'm going to go ahead and calculate a value for the reactance. This may take me a little bit. So let's see. All right, I got 25 ohms out of this, approximately 25 ohms. All right, I'm going to go ahead and find this angle now. There's the phase angle between the current and the input voltage here. So the tangent of that angle, I guess I'll write it right here. The tangent of the angle phi is going to equal, now if I do the same thing here, remember that this is equal to I X sub C minus I X sub L. This is equal to IR. So when we take this over this, what we're going to, the currents will divide out, and what we're going to have is X sub C minus X sub L over R. So that's going to be equal to 53 minus 37.7 over 20. So give me a moment here. I'm going to calculate that angle. I got 37.4 degrees for phi here. Now, if this were in a textbook, you might see something like phi equals negative 37.4 degrees, meaning that the angle here is behind the current here. I knew that from my picture here, so I went ahead and just used positive value here, positive value here. The angle between the voltage and the current is 37.4 degrees, and I can see by observation that this is a capacitive type circuit. Let's talk about average current. So here, if I use the RMS voltage, we're going to have 120 volts equals I times the impedance of the circuit, which is 25 ohms. I can calculate the average current. This is going to give me the average RMS current. I get about 4.8 amps. All right, so we've got that done. We've got that done. Power for the circuit, so one more calculation. I'm running out of room here. Let's do that right here. So power can be written current times voltage times the cosine of the phase angle between the voltage and current. So that's going to equal 4.8 amps times 120 volt. Again, that's RMS voltage times the cosine of 37.4 degrees. And I get, give me just a moment, okay, I got 458 watts approximately, or 0.458 kilowatts. So there's the power for the circuit. Important points of working a problem, an AC circuit problem. You got to understand how to do the phasor diagram. In order to do that, you have to calculate the reactance of the capacitor and the inductor. So for the inductor, the reactance is omega L, done here. For the capacitor, the reactance is 1 over omega C, done. Now, noticing that the reactance of the capacitor is larger, that dictates the type of circuit. That means that the voltage, average voltage across the capacitor is going to be higher than the inductor, and I'm going to take that into account in the phasor diagram. So, next important thing, drawing the phasor diagram. I always start with the current and voltage phasor across the resistor because these are always in phase. This is kind of like my anchor in the problem, I guess, so to speak. Then I typically draw the inductor. Remember that the inductor voltage leads the current. So that would be like up and left. The capacitor voltage lags the current. That's down and right. What I usually do then is compare which one of these is larger. And then replace the pair with the vector sum of the two. So in this case, the capacitor had the larger reactance. So that means that the net voltage is down and right and equal to the difference between the capacitor and the inductor voltage-wise. Then I take that phasor and move it over here for the vector addition, because remember we add vectors, tip to tail. And then here's the net voltage phasor. So this is equal to the input voltage here. Now what we do is use Pythagorean Theorem. The input voltage squared equals I, or V sub R squared, plus this quantity squared. Then you just replace each term with IR, IX sub C, IX sub L. And typically you can calculate your reactance. Or maybe your reactance is known and you can calculate something else. But typically at this point you should be able to calculate something from this part of the problem. And then to get the average current, just use Ohm's law. V equals IR in general, but we use Z. Z is the total impedance of the circuit. I like to think of it as the total resistance of the circuit when you take into account the resistor, the capacitor, and the inductor. So that's pretty well it. I hope this example helps understand how to write equations and analyze AC circuit problems. Have a great day.